So what we have left with is the fourth term, which is the pressure strain rate term. So what did we call this? I think we used either phi ij or pi ij term. In literature you will see both the symbols being used. Okay, so the pi ij exact, we have a formulation p prime by rho dou ui prime by dou xj plus dou uj prime by dou xi average. So this is something that requires to be modeled because this is a redistribution term accounting for anisotropic nature in the flow, or at least I would not call it anisotropic, at least it handles the two component limit, and it also tries to drive the flow towards isotropy because it is redistributing. Without this term, anisotropy is large, right? Let's say the production is only occurring in one direction, then isotropy is much more large. This term tries to drive the flow, drive the turbulence towards isotropy. It removes turbulence in one direction and distributes to the other direction, tries to make the flow as isotropic as possible. It's still not isotropic because there is production rate, there is dissipation rate, which is driving the flow still to anisotropic state. But this one is working against that. Okay. So now entire modeling idea here, okay. So modeling anything, this is not applicable to only this term. So modeling implies relating unknowns to knowns. Of course, using some arguments that make sense, of course. So what is the unknown here? Unknown is this particular term. What are the knowns that we have? Right? So pi ij is the unknown. So what is known? What do we have access while solving Reynold stress model? Reynold stresses we have access. So knowns are ui prime, uj prime, average. Have access to this. What do I have access to? In addition to that, I am solving seventh transport equation. So I have dissipation rate. In addition to that, I am solving the mean momentum equation. So I have the mean strain rate also. I have access to dou I bar by dou xj. So I essentially have access to this. This is the knowns I have. So I somehow have to establish a relationship between pi ij and this. Okay. So you can see the contrast here. It's the fluctuation of, so it's a gradient of velocity fluctuation and its correlation with pressure fluctuation, and how it is related to Reynold stresses or dissipation rate or mean strain rate. We will see. Somehow we will come closer to it. Okay. So to establish that, what is that equation which relates pressure to velocity? Is there an equation that you have learnt? Poisson equation, right? So this you would have looked into in your fluid mechanics classes, or at least in the CFD classes it has been taught. So let's look at that one. So we need a pressure fluctuation P prime, right? So what I need is, I need a Poisson equation for P prime. You would have seen a Poisson equation for pressure, instantaneous pressure itself. Now I need it for a pressure fluctuation because that is there, and I need to slowly move towards its correlation term also with the velocity fluctuations. So to get this, the procedure to get this is essentially similar to you derive your Poisson equation. You have to take divergence of your Navier-Stokes equation minus the divergence of your Rance equation. Just like the way we derived equation for fluctuating momentum, right? We derived an equation for ui prime. For that we said we take Navier-Stokes equation, decompose, Reynolds decompose, and then from that minus of we took the mean momentum equation to get transport equation for ui prime, right? So, so we will do that also for to get the p prime equation. So how we'll just start with this part. So first we take this part, the first one. So it's dou by dou xi of the left hand side of your Navier-Stokes equation, which is dou ui by dou t plus, or I am adding this divergence term everywhere. So dou by dou xi of dou ui uj by dou xj, your advection term. I am taking the conservative form here, okay, equal to the dou by dou xi of minus dou p by dou xi, okay, minus 1 by rho, okay, the density is, I left it, minus 1 by rho dou p by dou xi, and I have the viscous part, which is nu dou by dou xi of dou square ui by dou xj dou xj. Okay, so now I readily see that this I can interchange here. I can first differentiate with respect to xi and with respect to t, correct? So I can differentiate this with respect to, I can do this, differentiate first with respect to the xi and then the time. So that makes it, this go away, right? So goes away due to continuity. This term survives, and then this term obviously survives. The last term again the same thing. I can first differentiate this with respect to xi. So if I rewrite this, actually this particular term is nothing but it's dou by dou xj of dou ui by dou xj, correct? Dou square ui by dou xj dou xj. So now I can rewrite this as dou by dou xj of dou by dou xj of dou ui by dou xi. First differentiate with respect to xi and then the j, then again going to 0, continuity. This equation you would have derived before, how to get a Poisson equation for instantaneous pressure. So I have these two, a Laplacian for pressure and a complicated source term, okay. So we have Laplacian here, Laplacian term for the pressure, and this is a complex source term. Why do I call it complex? Non-linear term is there here, okay. So I have non-linear. This makes life difficult for those who are working with incompressible flows. If you are working with compressible flows, you have an equation of state relating your pressure to density and temperature for an ideal gas, or you can use thermodynamics to get different, for a different types of gas property, you can still get an equation of state for a dense phase gas and so on. But for incompressible flow, this is the only way you can relate your pressure to the velocity computation here, and you have a non-linear source term. So just put your hat as a CFD expert and then you will see the complexity here. You have to solve this for pressure numerically by discretizing this equation where there is a non-linear source term, and this those who have experience solving this know that this is the most computationally expensive part in your Navier-Stokes calculations. That means the velocity calculations for UVW wouldn't take much computational effort compared to this. It's probably 1 or 2 orders of magnitude larger. Okay, let's say you would require 100 iterations to get pressure converged this Poisson equation, but you probably need just 1 iteration to get your velocities converged. So you are just waiting for this to done. So it requires massive parallelization techniques. Anyway, so the Poisson equation is there for this particular component. So now I can decompose this, apply Reynolds decomposition. So I can say apply Reynolds decomposition. So I get essentially 2 by dou xi dou xj of this part, which is ui bar plus ui prime, again uj bar plus uj prime, equal to this term which is minus 1 by rho, density is constant, so dou square p by dou xi square, the p of course I say p bar, and then I also get this term which is dou square p prime by dou xi square, decomposed into a mean pressure and fluctuating pressure term. So I get here 4 different terms here, right? So I get dou by dou xi dou xj of first I get ui bar uj bar plus dou by dou xi dou xj of ui bar uj prime plus dou by dou xi dou xj of ui prime uj bar plus dou by dou xi dou xj of ui prime uj prime, equal to the right hand side part. Okay. So of course now we have to do the other part, which is the divergence of the Rans equation. Okay, so this is one equation now here, so I can take, just taking this, copy and then paste this. Okay, so I call this equation 1. Now I need to do the second part, which is the Rans part here. So again I would get dou by dou xi of dou ui bar by dou t plus dou by dou xi of dou ui bar uj bar by dou xj, equal to the right hand part, which is dou by dou xi of minus 1 by rho dou p bar by dou xi plus I have the 2 stress terms here, one is the viscous, one is the turbulent stress term. So I would get nu dou by dou xi of dou square ui bar by dou xj, and then I have this minus dou by dou xi of I have the dou ui prime uj prime average by dou xj, right? So this gives me the equation 2 here. But of course I can get rid of some terms before that. Again this interchanging here, again I get dou t dou xi, so this term goes away, continuity again. This term survives, the nonlinear source, pressure Laplacian survives, the viscous goes away and again, right. So I can say this is dou xi here and this is dou xj, again this goes to 0, same as previous argument, continuity. So 3 terms survive here. Okay. So this is my equation 2. Now I need to subtract 1 from 2 and do some more rearrangements to get an equation for p prime. We will see this in the next class.